In this session we finish off the initial description of the hydrogen atom. We'll come back to it in chapter 7, we're only in chapter 4 at the moment. In chapter 7 we talk about angular momentum, all the quantum mechanics of angular momentum and spin and whatnot. But there's still, what, 2/3 of the board on this old, what will soon become the old board, the second board. I will take the third board very probably tomorrow, much bigger one, almost, I don't know, 1.5 twice the size of this one. I'll have more options then. I'll be able to, I don't know, I'm not sure. It'll evolve, that's for sure. Alright, this chapter is a bit of a rag bag. Like it's a collection of topics. They all have the theme of solving the Schrödinger equation, so you know they have something in common. Like the first topic, which we've done already, was on simple harmonic oscillator. Now we're doing the hydrogen atom, and I'll start here on our next topic, free particles. And after that will be scattering, and then tunneling, and finally many particle wave functions. So a bit of a rag bag, yeah, just topics is thrown together in that chapter. And the next chapter will be scattering in 3 dimensions. You know, when you're shooting particles at targets and so forth. Very big business, literally, especially at the most famous atom smashing machine in the world in Switzerland. The famous LHC, the Large Hadron Collider, that a week ago discovered officially the existence of the Higgs boson. And stay with me a couple of years. I'll give you all the theory of the Higgs. Well, I can show you. Well, I'll give you 2. Here are two of the textbooks that I'll be using at what level is this? That's M1 or M2 level, probably more M2. And well, this is on string theory, supersymmetry and string theory, so that's probably PhD 1 level. So stay with me, and you can learn all about the theory of the Higgs boson, why it's so important to the so-called standard model, which is, well, don't worry about it. Okay, firstly, let me make a correction. You may remember in the previous session I was puzzled about it seemed as though something was missing in the Schrödinger equation. The radial, the radius, the r part. I thought there was a missing 1/r². Well, there was. So here's the correct form of the Schrödinger equation. What was missing, the little arrow indicating, what was missing was this 1/r². I did not have that in, I just copied it incorrectly last time. So that's the way it should be. So please make note of that if you're studying this properly. Alright, well, moving on. We've found a formula for the general energies of the hydrogen atom. So what we'll do now is find the specific energy level, the allowed energy, for the ground state, the ground state energy, the lowest possible level, and then we'll find its corresponding eigenfunction, you know, its wave function, u here, and then we'll find some average values, you know, the usual sort of stuff for each system, quantum system that we examine. You know, we want to find the eigenvalues and the eigenfunctions. In this general context, the eigenvalues are energies, pretty well. Now later we'll have eigenvalues of a different kind. They won't be energies. They'll be angular momenta, spin, stuff like that. Yeah, other things. These quantized values, when you have more, not just energies that get quantized, but other things that get quantized, they tend to be called quantum numbers. Right? So the different kinds of quantum numbers, like energy, spin, and quite a few others. There's quite a list. All right. Well, let's let's find the eigenvalue, the energy in this case, for the ground state, the lowest possible energy. That was when n is 1, k is 0. Well, you may have the form from the general form when you had En, we had an n squared down here. Well, n's just 1, so the n just disappears. And you can plug in the values for all these constants here, and you get minus 13.6 electron. The EV here stands for electron volt. It's like a unit of energy. And why giving this? Well, it allows experimental confirmation, right? Well, I've rubbed it off, but previous session in big letters here had hydrogen atom. Now that's about the real world, right? So the theorists, the quantum mechanics, the theorists who do this stuff, they would very much like to know whether their theories make sense. Meaning, do they agree with nature? Does the experimental result correspond to the theoretical result? That's important. So since we're dealing with the hydrogen atom, hence a real-world system, a real-world atom, the simplest one, hydrogen, it would be nice if the predicted values of certain quantities, in this case the ground state energy, corresponded to reality. Now the theory says the ground state energy should be minus 13.6 electron volts. Now that's testable. You can go out into the real world. That's the essence of science, of course, is to test your hypotheses. It's not enough just to have a hypothesis and not bother testing it. I mean, your hypothesis would be completely wrong. The best knowledge generating device that humanity's ever invented was science, meaning going out into the real world and actually testing and measuring and observing your hypotheses to see if they work or not, right? So this is the predicted value, and it's called the ionization energy. To ionize, what does that mean? It means to make an ion, I-O-N, out of an atom. And what does that mean? It means to charge the atom. Usually, well, there's two ways you can do it. You can rip off an electron, and so then the atom is no longer neutral, it's no longer zero charged, some. The nucleus is positively charged, the electrons are negatively charged, and for each, the neutron consists of, let's say, N, or let's say P protons. So the charge on each proton is equal in size, but opposite in sign, opposite in kind, if you like, from the charge on the electron. So normally an atom is neutral, meaning that the charge from the protons, so P times the electronic charge, but positive charge, equals the equal number of electrons in the atom, but negatively charged, and the two charges cancel out. So to ionize means to pull off, well, there's two ways, to pull off an electron. So the atom is now missing one electron. So it will be positively charged, because there's now one more proton than the number of electrons, because one of the electrons has been ripped out. Okay. Now for the, and the other way is to add an electron. So then the atom is negatively charged because it has one extra electron. All right. So in the case of hydrogen consists of one proton, no neutrons. Well, it can, but in a special case. So normally one proton and one electron. Okay. So to ionize a hydrogen atom means just to rip off the electron. Now, to do that, you need to supply this amount of energy to take it to take the electron far away from the nucleus, to zero energy. And we talked about that previous session. V, the potential, was zero at infinite distance from the nucleus. So this is the amount of energy you need to pull an electron away from the nucleus. That takes energy because the two are attracting each other, right? Opposite charged. And you can measure this amount of energy to strip an atom, to take off an electron from an atom, and it agrees with this very well. Ta-da! Another big event, right? may not sound like much, but when experiment and theory agree for the first time, when you hear that a theoretical result agrees with experiment, it's exciting. It means you're on the right track, that your theory's not garbage. So when this was confirmed, very exciting for the quantum mechanics and the theorists. All right. So experimentally okay, it agreed. So very nice. All right. So we have experimental confirmation of the ground state energy. Now, what about the ground state itself? The wave function, the U. Well, what is it? Well, at the ground state, n is 1, so k is 0. So that means that your f, your polynomial in the formula, the general. Remember the not U naught, but just U in general. The waveform for the hydrogen atom took the form of f, which is the polynomial in rho, times exponential minus rho over 2. At the ground state, when k0 ends 1, your f is just a constant. Right? It's a polynomial that's just a constant. So therefore your wave function, your aggregate state, your ground state, because we're talking lowest energy state, will be of this form, right? There's some constant here. Now you can figure out what that constant is by normalizing. And how do you do that? Well, let's say this point here, that's your nucleus, and the electron, and we're talking spherical symmetry. So imagine now, so here's your nucleus, that's the center of a sphere of radius r. And imagine now that this sphere gets bigger and bigger and bigger. And so somewhere in this infinite sphere is the electron. So the probability of finding the electron in this infinite sphere is certain, right? It's 1. So, so you normalize this, so it'll just be this is the probability density, right? So if you multiply it by the volume that it's in, that gives you the probability. So remember, probability density is what's the for a given volume, what's the probability of finding the particle in that volume, okay? Times the volume itself. That gives you the probability of finding it.